Hello, I am Ecem Dilek and I will talk about my term project for the course Machine Vision from Middle East Technical University. This is about color constancy. Color constancy is the perceiving colors from different illuminations without the color of the illumination. For example, here we can see a bottle which is slightly reddish. Here it seems to be white, and here it seems to be purple. In fact, this is all the same bottle under different colors. For example, here the color is turquoise, so we perceive the color more reddish, and similarly for the others. As humans, we can easily detect the color of the illumination. However, in machine vision, it is not simple as this. In machine vision, the aim is to find and extract the color information independent from the illumination. In fact, this is also a problem in camera industry because we want to automatically extract the color of the illumination without user intervention and fast. This is called auto-white balancing algorithms. Although the color constancy is about recovering the real world behind the image, white balance algorithms is about producing the best image from the best illuminants with aesthetically pleasant images. And here I will talk about an algorithm between color constancy and auto balancing algorithms, which is called Fast Fourier Color Constancy. This is being between color constancy and white balance algorithms is important because learning-based color constancy algorithms are very accurate, and white balance algorithms are practical in mobile phones, for example, because in the phones, the algorithms should run 30 FPS, because it's also doing a face detection or auto exposure, anything which comes to mind. First, I will talk about conventional methods. Here it is gray world assumption. This is the simplest algorithm, which assumes the color of the illuminants on average is gray. So we can talk about color histograms and color distributions. Also, this can be extended to statistical models and learning distribution models, etc. First, I will talk about convolutional color constancy, which is by Jonathan T. Barron, who works at Google. Here, in the essay, convolutional color constancy, he talks about how to construct an image from true colors and illuminant colors. We basically multiply it. Then we define some parameters, measures for chrominance of U and V, which are log chrominances. Also, we define a luminance measure. When we didn't care about scaling of W, which is the true color, the problem of estimating L just simplifies to estimating the chrominance of L, which is defined as logarithm of LG and LR. When we define LU and LV in chrominance algorithms, such as I and V, there is just a simple relation with image, luminance, and true image, just a subtraction. And because this is a linear relation, we can make our calculations faster. After assuming L is a unit norm, we can recover the RGB values from very basic relations such as here. But before that, I want to talk about what does it work for us. Here, the true image is seems to be a little greenish, although in true colors it doesn't have this green effect. When we plot the histograms, color histograms, we see that the input image has a translated version of the true image. Also, when we look at from a tinted image for the like reddish image, we see that the illuminance seems to be shifted again. Using this translation information, here the histograms are constructed, and the change in histograms, the translation, is learned for the for each image, learning the true illuminance, such as saying the highest score of the illuminance, a rating matrix will be constructed. For example, here the histogram is called M, and it shows the number of pixels in the image whose chrominance is near U and V. When we just sum them up, the histogram weights are constructed. N is the normalized version of the histogram. Then when we filter N with a filter called F, we can find the best illumination, which shows the highest score from this optimization problem. Then we continue with Fast Fourier constancy. The difference between convolutional color constancy and Fast Fourier color constancy is actually dividing the image and summing it on top of each other. For example, this image is three times larger in both sides. When we divide it by 9 and sum it on top of each other, we have this Elias image. In convolutional color constancy, the aim was using this and using its histogram to find the color of the illumination. However, here we use a smaller image, although it's a superimposed image. It is easier to find and it's cheaper to find the best illuminance. We calculate the image just dividing the larger image and summing it on top of each other. So let's assume this is the input image and it has this kind of histogram. When we divide it into smaller images and sum it on top of each other, the histogram is similar to this. We assume that the best illuminant is the illuminant closer to the gray, so we choose this one. This is called the aliasing, and we find out the best highest score illuminance for highest score of the color of the illuminance. Then we subtract it from the input image. We have the output image here. Thanks to the writers, and they have shared all of their code. You can just download it from their GitHub address under FFCC. But to make it work, you need to do some pre-processing, let's say. Everything shared here includes data, processing, and any kind of code you want to duplicate their work. I think it is run on Linux, I guess. So names of the files, directories should be changed a little. Also, script folder doesn't work for me, so I changed it also. Three main codes are here. Tune works to tune the learning parameters for each data set. It's one of the images, find the best element, and compares it to the true image, and gives an error here. For example, this was for Canon 600D, and you can train for your own data sets. Also, there is a visualize option that you can use their already existing data and visualize what they have done. Another note here, this code here, all of it depends on a mean function written by Mark Schmidt, so you also need to download it and add it to your path, otherwise it doesn't work. What I want to show here is the output images. Let's go from here. Because I don't have good cameras and I don't have this green color in my room, I just edited some of their input images with my name on it and run the algorithm again. For example, this was from Canon 600D camera, their datasets taken by Canon 600D. The image has this kind of a histogram, so it is green here. When the predicted image for the image for this input image is shown on left, and the true image is shown on right. I've tried it with writing my name in different colors as well. For example, when I use the red color, and the expected and the predicted color is more pink, but not red. But using white doesn't change the color drastically, actually. So this is what I want to talk about, Fast Fourier Color Constancy, and how it is different from convolutional color constancy and gray world assumption. This is really fast. It takes just a few minutes to run over all 400 images maybe. And the error values are almost 5 to 10%. Let's turn out this one. 12 to 13 to 12% better. It's more accurate. Also, the technique is said to be faster than the state of art. It was really fun to work on this project, and I learned a lot about color constancy and how it really affects our image. For example, my image seems to be blue, but here I'm not blue at all. So thank you for listening. If you have any questions, please write below.